Welcome back, dear friends. We're getting closer to our social party, but before that, we have two more talks, so stay with us, please. Next one, about sandboxing and isolating different processes. Ignat Korchagin will tell us more about this particular subject. Please welcome Ignat, the stage is yours.
Thank you. Hello, folks. Thank you for coming to my talk. My name is Ignat. I work for Cloudflare, and today we're going to talk about Linux sandboxing and how to do it with writing no code. Right? This is the official tech internal slide. Like, this is my header slide. You can see like an orange clown penguin in a sandbox. So who here knows about Cloudflare? OK, cool. Yeah. So then I'll skip the Cloudflare part and talk a little bit about myself. I do Linux in Cloudflare. Like, we are responsible for the operating system we run in production. I'm passionate about security, cryptography, and systems performance, and I really enjoy low-level programming, the Linux kernel, network drivers, bootloaders, and other stuff written in unsafe languages like C. I'm also a die-hard Linux fan, and I know a lot about Linux. That's why I'm presenting from a Mac today. So if you're on Twitter, you might know me from this video. I like to compare Linux operating system to Bentley. If you didn't see it, please go check it out. OK, so let's talk about sandboxing. Sandboxing in Linux is done via seccomp, but to understand seccomp, we need to understand the concept of a system call. Who here knows what a system call is? 50-50, OK. So yeah, these are the modern operating system, right? So in the modern operating system, you have your hardware layer, and basically, then you have your operating system on top. It's usually multitasking, so we don't run our software bare metal. We're not savages, right? And these multitasking operating system can have this many applications running on top, and this is where we separate between the typical user space and kernel space separation, right? So if we zoom in the interaction between the application and the operating system kernel, right? So what are system calls then? So system calls, the application needs to interact with the kernel, and the system calls is just like a set of interfaces, basically a kernel API, how an application can interact with the Linux kernel. So a system call is just a simple, well-defined interface between the user space application and the operating system kernel. It provides you with hardware-independent abstractions and some basic operating system services like file I/O, network access, time, sound, etc. So, for example, if you want to write some file to a disk, you really don't care on which hardware do you run. If you use an SSD or a spinning disk or NVMe, right? So you just write files, and the operating system abstracts that access for you. Same for network access. Also, like operating system being in between, it can provide you some benefits, like middleman services, it also enforces access control lists and different permissions, so you have privileged, less privileged application, etc., etc. And also, the task of the operating system is resource management. So because we have now many applications running on the system, right? So the operating system needs to share resources relatively fair between these applications. OK, clear with system calls? So what is seccomp? Seccomp is just yet another system call on Linux. But it's a little bit special in a way, because it provides a way for the application to notify the kernel which other system call it intends to use, and sometimes it's more importantly which system calls it will definitely not use. And when the kernel gets this information, the kernel can enforce the system call policy defined by the application. So basically, in a nutshell, seccomp is a tool for an application can use to confine or sandbox itself. And this is clearly written in the command page. It's not a sandbox in its own. It's just a tool to create sandboxing. So again, going back to this picture, so where does seccomp come into play? So seccomp allows you, the application, to establish some sort of contract to the kernel, right? And in this contract, the application, so by default, basically, the kernel has no idea what your workload does, right? But with this, the seccomp can provide this contextual information. So it can tell the kernel which system calls it intends to use, and it can also tell which system calls it will definitely never use. So for example, if your application just writes file on disk, it can tell the kernel, look, I have no intention to ever use any network access. So, yeah. And if the application later breaks this contract, the kernel is free to penalize the application for that thing, right? So like, by default, if the application later breaks that contract, well, the kernel will kill the application, will kill the process. And it feels a little bit counterintuitive for me as an application developer. Why would I risk my application to be killed by the kernel if by default I do nothing, right? So like, and I will be allowed to run. So like, I'm kind of adding more instability to my application in that sense. And for your normal workload, this is actually not very useful, but it's useful in a security scenario. So let's see an example here. Imagine you write a clock application, and it's a Linux application. And by the way, it should be on Linux because seccomp is a Linux-specific feature, right? So technically, what a clock application needs from the kernel? Well, basically, it only needs to know the time, right? So by using seccomp, the clock application can say, hey, kernel, I'm a clock application. I only need to use no time, so I will only use get time of day system call. And then the application starts. It needs to know the time. It issues the get time of day system call, and the kernel will reply with the time. It's OK. But imagine you were crazy enough to write this application in C, and basically some attacker got an arbitrary code execution in your system through their application, so your application has been compromised. So what the attacker will do, they try to, for example, steal your data, which your user has access to, and then they will try to exfiltrate it, right? So they will try to send that data to themselves. So they will direct the application to use the send system call. But now, because this send system call was not part of the original contract, the kernel will kill the application immediately and will prevent the data leak. Cool? So how to use seccomp? Everyone here knows what a uname command does on Linux and Unix systems, right? So you can just request like the operating system information. It's a very simple system call which just copies a string from the kernel to user space, right? So as an example, let's actually try to rewrite this tool, and like let's write a simple uname like toy tool, right? It's a complete program. You can copy, paste, and compile it, right? And what it does is basically two things. It issues a system call called uname to the kernel, gets a name from the kernel, and prints it to the user. So if you are to compile this application, you will see something like that. If you don't see Linux, by the way, stop following, because seccomp is available for Linux, and if your operating system is different, it will not work, right? Now let's go back to that code. Is it visible? Okay, fine. I mean, don't focus too much on the details. You will get the code later anyway, but just follow along. So let's try to sandbox this application. So let's add a sandbox function before our main workload comes into play, right? And then, just for the purposes of this function, let's implement a seccomp policy in a different slide. So a little bit scary, but I mean, don't bother too much on the details. The gist here is you write your policy in a BPF language, and actually it's not eBPF, it's classic BPF. So you write your desired policy, and for the purposes of demonstration how this technology works, we will actually write an invalid policy. We will actually write that we will allow every system call except the uname one. So we will say in this policy, if the application tries to call the uname system call, you can also tell the kernel not to kill the application, but instead return an error code, and custom error code, and you can select the error code whatever you like. And then you call the seccomp system call, provide the policy to the kernel, and from that point, the policy is enforced. So if you basically recompile this application with this function and try to execute it, you will see this. So you see that uname system call failed, and you will see an error code network is down. And we clearly know this is because of our seccomp policy, just because the normal uname system call never requires any network access. So you would, in normal cases, you will never get such an error code from this system call. So yeah, in this case, because we instructed the kernel not to kill the application, but to return the error code, we kind of force the application going to the error path, and this is what we get. However, as you just saw, writing seccomp policies by hand is hard. It's a low-level assembly-like language, BPF. It's hard to write, it's hard to review, debug, and update. And you've seen the listing for just a simple policy which prohibits one system call. Imagine how that would look for a real production workload. And you also need to be aware of low-level details like system call numbers, and system call numbers, even though they might have names on in different architectures, they actually, different architectures have different numbers. So for example, if you write your BPF policy, seccomp policy for x86, it probably will not work on ARM. There is also some quirks, like setting no new privilege bit, which you can dig up in the man pages, but if you don't do it, there are problems. So if anything, when something is hard in Linux, people just write a library for it to make it easier. So we can actually, there is a library called libseccomp, which aims to allow you to write your seccomp policies a little bit easier, and we can actually re-implement our sandboxing function using the libseccomp, and you can see the listing is much shorter now. And the thing is, what you do, you call the library function, so you specify a default action. So by default, we allow all system calls. And then we add a rule saying if the system call is uname, and then we can reference it not by number, but by actual name, don't allow that system call. And here we will write a simpler policy, so we will not ask the kernel to provide a custom error code, just kill the thing. And then we kind of load that policy into the kernel. So from that line, the policy is enforced. So now, if we recompile the application, and because we're now relying on libseccomp, we have to link with it and execute the program. We will see this, and it's kind of like the shell will detect the application will be killed, and it will tell us bad system call with no output. Because now, remember, we didn't force the application go to error path. We just as soon as it tried to do uname system call, it got killed. Clear so far? So this brings us to no-code seccomp. As you just saw, even if I want to write seccomp policies, I have to do it in my code. So either I'm using library or not, I have to add a sandboxing function to my code to add these sandboxing capabilities. So how many developers, who here is a developer? Yeah, many developers. How many developers start a project with a mindset that most likely I will write bugs and security vulnerabilities, therefore the first thing I do is to sandbox my code? I don't believe you guys. Well, maybe, yes, if you're burned like several times on it. So most time, like nobody does that. Like we'll write functionality and stuff, and like even most like popular open source projects don't have the sandboxing support. And this is the problem with seccomp, that the seccomp applies the rule of the policy you design only to the current process. So it is expected by this feature that developers will sandbox their codes themselves, but there kind of no official external interface to apply a seccomp rules to a running process already on your system or to a different process. On the other hand, you have like operators, security engineers, sysadmins, which want to actually sandbox other applications in production, but they have almost no control of the seccomp policy, right? And also, like, open source is great, but there is still like stuff we run which is proprietary, or for whatever reasons we don't have access to the source code. So like there is no way to sandbox. You don't know what that code is doing, and it would be nice to sandbox it, but you don't know. You don't have access to the source code, so you cannot sandbox it. So this is the gap, right? So the gap is, from one side, you have the developers who can sandbox their code, but not incentivized to do so. And from the other side, you have operators, sysadmin, security engineers who want to sandbox all the applications, but don't have the capability to do so. So this is why sandbox with no code is kind of important. How do you do that? And one way to do that is actually, you can do it with systemd. So if you run your services through systemd and use systemd unit files, there is a directive called filter, where basically you can provide a list of names, of system call names, which your application is allowed to execute. And if not, like the application would be killed by default. And yeah, it has really good documentation. So we can actually let's see how it works. So now we recompile not our sandbox, but the original application with no sandboxing function. We can verify it still works. And now we can simulate running it through an ephemeral systemd unit, and we can still see it works. OK, so we still see the expected output, and the error code is successful, right? Now we can rerun it with the system call filter definition. So in this case, I'm providing a list uname, and the tilde in front basically inverts the system call policy. So by default, it's an allow list, but now it is a deny list of. And in this case, we see that the application did not run successfully. It was killed with a signal, and and there is no output from the application. So we basically made the application work. We sandboxed the application without modifying its source code. And with systemd, there is another director called system called error number. You can actually tell the kernel not to kill the application, but as we did in the first example, return a custom error code. And here we now see the application has the capability to provide the error output, and the error code is what we set. Its network is down, and the application was not successful. Cool? Finished early, right? No, there is more to it. So but there is always a button, right? So there is this small print with systemd. If you go into the man page, that some system calls are always allowed. Even if you specify them on your deny list, they will always be allowed. And one of them is, one of the dangerous one is actually the first one, execv. So why execv is bad? For what? Well, yes. Well, basically, the thing is why execv is so bad. So like imagine, let's go back to our clock application, and we have the attacker who compromised our application. So what is the first thing the attacker will do if they got like remote code execution on your software, right? Well, they will execute a shell, so it's very hard. Depending on the vulnerability, it's very hard to control the process itself, so you likely execute a shell and then do whatever you want. So that's why execv is the most dangerous system call ever, so you definitely want to block it if your application doesn't need it. And for this reason, because of this systemd cannot block the execv, we develop our own Cloud for Sandboxing toolkit, to inject seccomp rules into almost any process. And basically, it kind of follows the systemd approach, but takes it one step further. So it consists of two parts. One is a shared library for dynamically linked applications, and another is a launcher for statically linked applications. And the nice thing about it, now it can block any system call, including execv. And basically, it works on any binary written in any language, even proprietary ones. So oftentimes, you have even, like, it's cool, even if you have access to the source code, let's say you have a high-level application with Java who uses, like, whatever is more than now some framework. So, like, these developers do not even know about system calls. So how do you sandbox that application? And yeah, the best part, it's kind of open source, so you can go and take it and use it. But at this point, you should say, like, really, shared library? You said zero code. Like, isn't like coding against the library requires code? Well, no, it's a special library, and I'm going to show you. So again, let's take our original unmodified sandbox uname application, toy application. So it works as expected still. By the way, all these slides and code were copied from the real terminal. So it's like a demo which never fails. Yeah, so it still works. And now, to sandbox the application with our library, all you have to do is you don't have to modify the code, but you have to load the library into the process address space. And one way of doing this, you can use the LD preload on Linux directive. So what you do is you load the library into the process address space, and again, you can specify either allow list or deny list of system calls, and in this case, we will specify the deny list to the application. And then, before the main code executes, the seccomp policy will be applied. And now we can see that, again, we have the debug output from the library that it added uname system call to the process seccomp filter, and you see the bad system call because when application tried to call the system call, it got killed. If you're deep into Linux, you might be, preload is not that great tool. It doesn't work in all the cases. For example, if you have a set UID binaries, preload will not work. So an alternative, what you can do is you can use the patch elf tool and add the library as a permanent dependency to your application. And again, we are not recompiling the tool. We are operating already on compiled executable. What we just do, we add a dependency on the library to the process. And you can check that once what shared libraries is required, you will see that it now requires our application, and then you can actually run your library as normal and just provide the system call policy in the environment variable. And it will work as is, and you don't have to use LD preload. So this is for dynamically linked applications. What about statically linked applications, right? So if we recompile our application as a static binary, it still works, but you may discover that this trick doesn't work anymore, and you can probably not add you can probably can't add our library as a dependency because it's a static self-contained application. There is no dynamic linker involved, and the library will never get loaded. So for this, we have the second part of our toolkit called Sandboxify Launcher. So what you need to do, you need to rerun your application through the Sandboxify Launcher and basically, again, specify your desired seccomp policy through the environment variable. And we can see there is no expected output, and the application was killed. Cool. So Cloudflare Sandboxing tool is easily configured via environment variables. So the preferred approach from security perspective is to provide an allow list. So you provide an allow list of system calls you allow your application to use, and anything not in the allow list will cause the application to get killed. Sometimes it's very hard to do so, so you might as well revert back to the deny list. So instead of providing an allow list, you at least block the dangerous system calls like execv or mprotect or something like that. So anything is in the list is not allowed, but everything else is. There is also one other useful feature called seccomp default action, which is currently supports only one parameter, one option called log. So basically, sometimes you have the application, especially a proprietary one, and you don't even know what system calls it uses. So you can probably use a trace to figure that out. But if you have the toolkit, you can actually specify seccomp default action and set it to log. So what will happen is the kernel will check the allow list or deny list you provided, but any violations will not cause the application to be killed, but instead just the violation would be logged. So it's useful for a discovery phase. You can run your application for some time under the permissive, so-called permissive mode, where just you log all the system calls it uses, then you adjust your allow and deny list, and then you enforce it by removing this environment variable. And again, I'll repeat myself. So the sandboxing toolkit contains two parts. One is lib sandbox SO, which is should be used for dynamically linked executables. And you need to somehow load the library into the process. You can use either LD preload or patch the ELF binary directly to make it happen. And then you have the Sandboxify launcher for statically and dynamically linked executables. And you need to launch the executable through the launcher to make everything enforce. Clear? Easy day, right? So almost the end. Well, you might ask the question, why do the hell we need like the left part, right? If like the Sandboxify launcher is good enough for both statically and dynamically linked executables, like why do we even need that one? And the reason is, like, if let's review from a 1 or 10,000 feet view how a process is started on Linux or in any programming language. So when you start an application and process, you have basically two stages. One is so-called runtime init stage, where your runtime, which will depend on which programming language we'll use, will do its magic to allow your code to execute. And then you have the main logic. This is where your main function gets called, right? Yeah, and yeah, every programming language has its own runtime, including C. You have the C runtime. So yeah, but if you use the Sandboxify launcher, your seccomp policy will get applied before the runtime init stage. And if you use the libsandbox library, your sandboxing policy will be applied after the runtime init stage. So why is it? What does it make a difference? Like, so what is runtime init basically? Runtime init is a lot of system calls which are never used afterwards. So like every runtime does like some crazy memory setup, sets bits and pieces to make everything work, and then and then you will never use it in your main workload. So, for example, and if you enforce your policy after the runtime init stage, you need to only allow the system calls from your main logic, versus if you enforce your policy before the runtime init stage, you would need to allow the system calls both for the init stage and the main logic to allow the runtime init stage to succeed. So let's see the difference. Again, let's recompile our original non-modified application, and again, make it dynamically linked so we can use the lib sandbox SO. But now let's write a correct policy for it. Let's write a minimum allow list, which will allow our application to succeed. And in this case, if you run it in the log mode and see what happens, you technically need only 4 system calls for this application to work. So again, 4 system calls we allow, we get the output, and everything works successfully. Now, if we try to run the same application, but through the Sandboxify launcher, because the runtime init stage is included now, as you can see, we now need to allow much more system calls for the application to execute properly. And this is the difference for this particular case is either you have the 4 system calls in your allow list or 13 system call in the allow list. The less is better because your eventual attack surface will be much smaller, right? Cool. The last question you may ask is, what about performance overhead, right? So like by adding this filtering, what is the cost? And for this, I wrote a very simple benchmarking tool called PID benchmark. What it does is basically, like the simplest system call on Linux is get PID. So it's even simpler than uname because it copies a one integer from the kernel to the user space. So it's all very useful to benchmark system call performance, like worst case, right? Because the system call itself does not almost introduce any latency. So, and what this does is like it calls the getPid system call many times, and we just basically take clock measurement before and after it happened, and doing some math to see the result, right? And if we compile this application, and I was running it in my VM on our Kubernetes cluster, which is not very powerful, but not very not powerful. So basically, I get around 211 nanoseconds per system call, per get-PID operation. If basically I rerun it under seccomp policy with a minimum allow list, I get 235 nanoseconds per system call. And you will be just screaming, wow, it's like feels like 10% performance drop. Well, not really. It's actually, remember that the overhead of seccomp is kind of static per system call because like getPID is a very fast and simple system call. So you technically get, by installing seccomp, around like 20 nanoseconds performance drop of your system calls, which is many system calls take much longer than that, actually. Yeah, and I also wanted to explore how that performance drops if you add, like, is it dependent on the size of your allow list, right? So, for example, I rerun this program with the deny list, and I put like one system call in the deny list, which is not related to my program. So, for example, my program never uses execv, but I put it into the deny list, and I get kind of similar performance with the same 20 nanoseconds per system call. So it's actually kind of independent when your list is small. If you basically rerun the application and I add many unrelated system calls, so I want to block many, so I get around 1 additional nanosecond and 1 additional entry in the list. And this brings us to the case, and even like not only from security perspective, allow list is better. It's also better from performance perspective because in the deny list, the way your program is structured, it checks the system call number for each entry in your deny list, and then it goes to proceed in the good case. So in the good case, you traverse all the list of denied system calls. If you use the allow list and your workload functioning as it should, so you usually will exit the seccomp program much faster. So in this case, if you actually use allow list, it will be a little bit better. But still, like nanoseconds are, it's not even a microsecond domain. So nanoseconds are pretty much almost no performance overhead. Cool. I think this is all I wanted to tell for today. So here are some useful links, which you'll get later. So the first link is a link to the man page for the seccomp system call if you're interested in checking the details. The second link is a link to GitHub project for libseccomp, the one which I showed you in the beginning of the talk, and the one which is actually used in the Cloudflare toolkit as well. So it's a dependency. The third link is I repeat the link to the documentation for systemd, a seccomp filter directive. If you want to use it, consider reading it. The fourth link is the link to GitHub resource with Cloudflare Sandboxing toolkit. Please feel free to download it, use it, complain about it, but better submit pull requests if you need anything. Yeah, and the fifth link is basically everything I presented today and something a little bit more is written on the cloud for a blog post. So instead of this presentation, you can go there, copy-paste the code, and try it yourself. Thank you very much for your attention. Please use this QR code to leave feedback for my session, and I'm happy to answer any questions if you have left.
Thank you very much. Round of applause. Please raise your hands and keep them for a while so I can notice you. Let's start over there. George, please.
Hello, thank you very much. My question is the next one. There are many similar utilities, some like bubble wrap or FireJail. Can you please tell me maybe the major difference with your utility here?
Regarding FireJail?
FireJail, bubble wrap, etc. For example,
I heard about FireJail. I think it uses a different technology which is available not only on Linux called Chroot, which is also a useful sandboxing feature, but it's kind of like complementary to Sandbox. You can probably use both. I know a similar project. When I originally published this, I was pointed that Chromium operating system has a similar tool concept. I actually went and tried to use it, but it's not very, like normal distribution Linux friendly. At least at that point, it was very hard to rip it out and use it on any other Linux than inside Chromium. But in Chromium OS, there is a similar tool which does exactly what I described today.
By the way, bubble wrap project, it's used in Flatpak and it can use seccomp too.
OK, yeah. So I want to mention that, for example, if you use container technologies and you use Docker, Docker uses seccomp as well by default.
Thank you. Gentleman here.
Thank you. It's very insightful. I have a couple of questions. One is related to performance. So you've shown some metrics for different approaches, for natively built application with seccomp rules inside, and for using lib sandbox.so library or something. So you have two different tools. One which work before init, and the second which works after init. Are there any performance differences between these two solutions for statically built applications and for dynamically loaded?
There are no performance difference except for the ones if you have a different allow list or deny list. So like so the programs themselves, they're not part of the tool. They're part of the process. So what the tool does and what seccomp does is basically you either write your program yourself, your policy, or the tool kind of compiles it for you, and then you insert that program to the kernel. So like the program is not in the tool, the program is in the kernel in both cases. So and depending on the program size, you get these slight performance differences. So basically, yes, with Sandboxify, because you would have many more system calls in your allow list, the performance might be slightly worse.
Yeah, so init stage doesn't take so much performance. Yeah.
Sorry?
Yeah, init stage doesn't take so much performance.
No, it's a one-off thing when the process loaded, right? So like it's fire and forget. So like when you start an application, init stage passes, and then your main logic takes over, and you never go back to the init stage anymore.
Okay. And the second question is related to a more security-related thing. There are the same two approaches, lib sandbox and Sandboxify, or how it's called. And one of them filters init stage. The second one runs after the init stage. Mm-hmm. Have you ever met any security threats on the init stage, maybe?
Security threats on the init stage, I guess, I mean, this is a chicken and egg problem. I guess if your, for example, application compilation environment is compromised, right? So you might get injected some arbitrary code into the init stage, for example.
Okay, so if you have a compiled application, basically it can be somehow, I don't know, poisoned outside of the application.
Not compiled. Like if you compile your application in an environment which has been compromised. So init stage is generated by your compiler or tools like which compile and package your application, right? If that application can inject code, then init stage can be compromised, but as well as your main logic can be also compromised at that point.
Thank you.
Thank you. Here in the center, please. And any more hands, please raise them.
Yeah. Ignat, thank you very much for the presentation. Really insightful. I got two questions. First is, what's wrong with execve? What does it do, and why was it not blockable by default in the implementation of Lip Sandbox? What is the reason behind it?
Not clear. Systemd. It's allowed by systemd.
Yeah.
So, as I mentioned, execve is a system call which allows to replace the code of your process with another process. So, if I have a clock application which is very limited, right, I can replace it with a shell, and then I can issue arbitrary commands and get access to whatever the process has access to. Why it is allowed always in systemd? This is interesting. This is because systemd actually needs it, right? So, like internally, how systemd works, if you launch your application through the systemd unit, it forks itself and then calls execve to actually start your application. And that's why systemd cannot block that system call, just because it will not be able to start your unit. And this is why I think the decision is that like you cannot block execve systemd, because systemd will not be able to launch your application.
Yeah, thank you. And the second question, like 200 nanoseconds when you bring it like this, sounds like an eternity. But what are typical durations of other system calls, like allocate memory and stuff?
It's very, very, very platform dependent and very, very like architecture dependent and very, very dependent on like your environment. So let's say, I don't know, like with memory, it depends on if you have like 4 gigs of memory or 4 terabytes of memory, right? I don't know if some servers have 4 terabytes, but like we've seen even like without this, with the Linux kernel, the performance of various system calls differ if you execute them on the laptop and if you execute them on the server with like 512 gigs. So it's
well, yeah, but you shouldn't get milliseconds, right? You shouldn't get milliseconds, right?
Shouldn't get what?
Milliseconds.
Sometimes you get milliseconds. Sometimes, yeah. Like system calls may, for example, there are different system calls. System calls may put your process to sleep, right, and not return if you're, and you get milliseconds, seconds, whatever.
Okay. Thank you.
Thank you. Yes, gentleman in the center, yeah.
Your mic is seccomp, sorry.
Oh, okay, that works fine. So my question is really simple. Is it possible to implement mitigation about used allowed system calls via SE Linux or AppArmor?
Sorry?
So is it possible to implement the same mitigation via SE Linux or
SE
AppArmor?
So SE Linux and AppArmor are a different breed, right? So seccomp, you may think of seccomp as a system call firewall, which sandboxes the application. SE Linux and AppArmor are examples of Linux, so-called Linux security modules, which are operating deep inside the kernel. So basically, one tool, as I said, is a tool for developers. One tool is basically for system administrators to enforce the policy. But ideally, you should use both. So it's kind of defense in depth, and each of them have their pros and cons. So AppArmor, even though it's kind of, I have not much experience, but I know that you kind of package your policy with the application, but it goes deep inside the kernel, and it's kind of more of like system admin control rather than developer control. Does that make sense?
Yep, thank you.
Thank you. To the right.
Thank you for the talk. And again about execve and Sandboxify. I have a look at the sources and found that Sandboxify uses the same execvp to execute the actual process.
Yes.
And its use is after call to set up seccomp filter.
Yeah.
So Sandboxify also didn't allow me to exclude execvp, or it somehow bypass.
It's somehow bypassed.
Okay, then how it's done?
Yeah, I encourage you to read the source code. But OK, in the nutshell, it's a good question, right? Both systemd needs to execute the process, uses execv. And if you run through Sandboxify, you also need to execute the process, and you use execv. The difference is, like the first iteration of the tool used a technique called p-tracing, which is it still uses it, basically, which is basically a debugger. And in Linux, if you have sufficient privileges over your child process, which you usually have, you can temporarily suspend seccomp policy. So what the Sandboxify tool does, it sets up all the policies for the child process, then kind of attaches it as a debugger, suspends the policy, but sets a trap to return to the debugger right after execv. So it executes the target process, so the kernel sets up the target process, but before handing off to control stage, even runtime init, it flips back into debugger, and the debugger kind of re-enables seccomp policy and detaches itself. This was the first iteration. The second iteration, which I got a nice pull request, by the way, it still leaves you in this weird state where if you normally run your application, you will see in the process tree your application as a child of your shell, but then you see this weird, like Sandboxify your target application, then the Sandboxify exit, and your application is reparented to the init process. It's not great, so I had a pull request basically where a person flipped the sides. So instead, starting the target application into the child process, they do it from the parent process, and the debugger is the child process. So once that happens, the child process exits, the seccomp policy is enforced, but you have no garbage in your process tree.
Thank you. Another question here in the center, please.
Hello, thank you for the presentation. I think I like everything what Cloudflare do. I have a general question. Can you tell the most interesting case of using a library or launcher from your experience?
This library?
Yes.
Well, it's basically, I call it hunting for unexpected behavior. So what we do is we run some applications in the log mode continuously, even though we don't want to sandbox them. And then eventually, I can scan the logs and see that, OK, for example, I had a Go service which was perfectly sandboxed, and then it started spewing in logs, reading some random file on the file system. And it's almost like a security threat, and we put it like, oh, somebody's trying to exfiltrate us. But then we dig it through, and one of the transitive dependencies added a code which reads some arbitrary config file once a day or something like that. So we actually caught it, and it was dependency of dependency of dependency. So it kind of was a legit change, but it's still interesting how much visibility you get just by doing this.
Thank you.
Thank you. Any more hands? There was plenty of them. 1, 2. Yes, to the right. Last one.
At first, thank you for presentation. And my question is it possible to apply the policies not on the start, but in some kind on the middle of the main code?
This is a good question, yes, and it's definitely possible. And the nice thing about Sandbox, it's kind of stackable. Sandbox programs are stackable, so you can further restrict your application, but you can never relax policies after the process started. And actually, you don't only have to use this tool. So for example, if systemd sandboxing is OK for you, use that, but then use this tool to additionally restrict only the exec system call. And this is basically how many applications actually, security-aware applications, what they do. So they, for example, they start the code. It's similar to dropping privileges, right? So like if you need a privilege port, you bind to a privilege port, and then you drop privileges. You start in privilege mode. You can do the same in seccomp. At the beginning, you need a lot of things. So you have a very relaxed policy. You grab all the resources you want, and then you restrict yourself. Then when you need want to restrict even more, you can do that down to the very bit. And it's worth mentioning that libseccomp and this tool, and a typical approach is just allow listing or deny listing system call names, but you can be as granular as write seccomp policies with arguments. So for example, if you need only one file, you don't need to restrict yourself from opening, or you can even restrict reading and writing. So you open that file. Once you get the file descriptor, you can write yourself a seccomp policy, so you only allowed reads and writes if the argument is that file descriptor and nothing else. So you can be very, very, very strict.
Thank you. Thank you very much, Ignat. A round of applause for our speaker. Find him in the hall. Thank you. Thank you very much.